Okay. Well, welcome. Good morning, everybody. My name is Shervin Merriar. I'm really excited to give this talk titled Biomedical Ontology Matching Using Relational Graph Neural Networks with RDFs metapaths. And this is a collective group of Master of PhD students from Maastricht University, about 2 hours south of Wageningen in the Netherlands. So just to give the background motivation for this problem, so you just saw the use of ontologies in multiple industries, agriculture, what have you. Pretty soon, if you work with those, you will get to a problem that you have all these vocabularies and ontologies, and you wonder, what do I do? Like, how do I connect these? What is this node in the other ontology? So this is what the context I'm giving the talk about. It's about identifying semantically related concepts between multiple ontologies. Okay. Right, and then yeah, and then there were a couple of tutorials yesterday of use of LLMs for doing, writing Sparkle, or also doing things of this nature. But again, if you look deep underneath these LLMs use embeddings. So this work is kind of putting both of those together. So I hope that makes sense. And to the right, I'm showing kind of how this could be challenging, because not only you're finding alignment of references between two different types of ontologies, but these ontologies by design could have different structures, morphologies, and there's a lot of discrepancies to do that. But also you still want to use the abundance of information there is, right? You don't want to ignore that. For example, yeah, of course you can do a lexical search and just do, this matches that, but then you're losing a lot of context. Yeah, so we're proposing here integrated contextual and structural knowledge, as well as heterogeneous entity type of model using these R-GCNs that I will introduce shortly. Again, just to look at the broad picture, to just do this, there's kind of three overarching paradigms. And one is like where you can have like multiple sources and try to have like a common ontology to map all of them, but here you're going to lose the local granularity of your representations. So then, in the second paradigm, you kind of can do pairwise, but this quickly can get complicated. You will maintain local your granularity will be preserved, but again, if the idea is that maybe these ontologies are being developed and evolve independently, that's become challenging. So the third paradigm is kind of what we are adopting here, is where you have these pairwise, and on top of it, maybe you have some shared vocabulary. And this is kind of where we use this RDFs metapaths and you share, and some other terminology that we share between them, between the pairwise local alignments. So I hope that big picture makes sense. Right, so our use case is we're focused more on the clinical or biomedical ontologies, and providing, so this is from the paper that is being presented. So so yeah, you can. So I'm trying to show at least the complexity of problems still. So for example, the SNOMED is an ontology, biomedical ontology, and then the NCIT is another one, and we're trying to match these ontologies together. But again, like if you take the example of basophil adenocarcinoma, and you can see in one ontology that matches with a concept that is a little bit broad, a little more specific. It specifies the gland, the the pituitary gland, and then so these, if you just match those, it's you can see that, for example, firstly lexically trying to match this, it will fail because it's just not going to manage. So you really want to understand the structure where actually their parent nodes give you that kind of structural information or context that you need to know that these would match. So yeah, like I said, this is where the preserving the structure, understanding and capturing the structure, hopefully I managed to show you, is important. So I'll come back to this use case at the end and show you how this is solved. But just to give you an idea of some work that's being developed already in this field. So so people to capture also this structure and using RDFs RDFs and metapaths. There, for example, there's some work that uses RDF2vec to embed ontologies, and then they use sort of like transformers. They use unsupervised masking, multiple types of masking, and then they train their embedding model and their encoders, and then at inference time they use those embeddings to match them. So this is one type of work that's really inspired our approach as well. And then another more geometrically oriented embedding-based model is this absolute orientation that, again, they use RDF2vec and they embed different ontologies, and then they use this absolute orientation, which is a matrix of rotation matrix to match the nodes. Again, so this is kind of what I'm going to use as our baseline to compare our results to. And yeah, our intuition was that these approaches don't generalize well. So hopefully in our experimentation, you will see that we'll be able to show you what I mean by that. Excuse me. Okay, so there are many ways to do embeddings, and now these are slides I'm borrowing from a knowledge graph course from Maastricht University, and it shows you broadly what different types of knowledge embedding methods there are. And the approaches I showed you fall under the top left corner box, random walk-based embedding generations. The approach I'm discussing today is graph neural network based, and yeah, we're not getting into the other approaches, again, just to give you an idea. Right, so a little more about the way these graph neural networks work, in case people haven't seen this, and there's, again, this is course material. You may have link you may want to later maybe view yourself, but there's a couple of key ideas to these graph neural networks, and one is this idea of local neighborhood, and where vector representations of nodes are, for example, the target node A. Here we're showing is learned by message passing over these links and neighborhood nodes. And also these layers of message passing can be stacked over each other, and you can get as deep as you like, and this kind of expands your receptive field. And then the other key I guess, feature of these methods is that they share parameters. So when you train these models, the same parameters are shared on different parts of the graph. So this kind of improves their inductive bias. So in our case, this is useful because when we are embedding one ontology versus another, we use the same weights. So this is where we share the knowledge through the parameters that are trained. Yeah, so history of GNNs, this kicked off in around 2005, but really around 2015, 16, there was a paper that came out by Keefe and Max Welling, and this really, people following that, they started doing variations on top of it and adding attention, and then also all the way around 2019 is where these heterogeneous graphs got popular, and this R-GCN, relational graph, GCN or GNN that I'm talking about is a type of heterogeneous graph because these ontologies are by nature heterogeneous, and then so on and so forth, different variations, just to put things in context. Yeah, so last thing about the relational GCN is when everything I spoke about now, these R-GCNs basically respect the heterogeneity of graphs, as I just mentioned, where these message passing between neighbor nodes is done per relation type. So the neighbors are picked according to the relation neighborhood, and then there's a set of parameters learned per relation types, and this really gives them a real boost in, like if you're embedding knowledge graphs and multi-typed graphs of any kind of sort. So those are basically the features that really help us do this design, and our pipeline looks like this. There's again input graph, knowledge graph, or an ontology, and then we apply the graph neural network, and then we learn these embeddings, and then we use these as using a prediction head, and we can then evaluate these, train these, and design loss functions for them. So this is from the input to output. Okay, and our design, putting everything together, looks as follows. In the next couple of slides, I will show how this is done. Basically, we're taking two ontologies, embed them using an encoder, and then once the embeddings are learned, we use a decoder to determine the matches between relevant entities. So the encoder, the R-GCN for ontology mapping encoder, looks as follows. We take one ontology, and then now this is the GCN part that I was showing you. We put it in K layers of encoder, and then at the output of that, we have these node embeddings for a single ontology. And then the decoder is then takes embeddings from a pair of ontologies shown in red and blue. And then the job of the decoder is to, between the two entities, we compute a sigmoid function or a score function. And if it's above a threshold, then there's a match between the respective nodes. And then the last element that we added is these RDFs metapath rules that I spoke about. So in the experiments that are coming up, you'll see these R9 and R11 variations, and these are with respect to these rules, RDFs rules, and one is for membership, and the other one is for assertion, where, for example, if node A is a type of B, and node A is a subclass of B, B is a subclass of C, we also infer that A is a subclass of C. The second rule, R11, is when A is of type B and B is a subclass of C, A is also a type C. So then these are the two other variations that we added, and we think that when the complexity of the problem goes up, these RDFS structures really help to preserve the performance of the R-GCN, and I have experiments to show this. Okay, so getting to experiments, we use these ontology alignment evaluation initiative datasets. So they have tasks on using many ontologies. I'm not going to go through the details of like the statistics about the datasets, but there's a variety of them, from human disease ontology to anatomy to NCTI, cancer thesaurus, SNOMED medical clinical terms. So this is, we used, so this consortium has these alignment data sets as tasks. and we use the 2022 one related to ontology matching. Okay, so in terms of the metrics we're using, we use two sets of different metrics. One is for classification, like precision, recall, and F1 score as binary classification tasks, if there's a match or not between two nodes. And we also we use hit set K and mean ranking. This is for typical knowledge graph completion tasks. So we use these, and essentially they're looking at how many of these matches you correctly predict in top K, and what is the mean rank of that, of your predictions. Yeah, so this is the first set of our results. We divided the tasks to 3 separate experimentations. So DS1, the first task is where in each respective ontology, we only have the subclass relation, and between the nodes of 2 ontologies, we keep the all same as relation. So we then embed these, and we do it across 6 of those OAA tasks for pairwise ontology matching. And in terms of model, I'm using here the absolute orientation as baseline, which I introduced earlier, and the R-GCN and the variations thereof, the R9 variation, R11 variation, and R star is everything together. And then we're showing precision, recall, F1 score, and hits at 1 and 10, and mean rank. So just to summarize this, we really see that just the version of R-GCN, even the non, if you like, variant version, still outperforms AO, and this was our hypothesis that AO wouldn't really generalize to multiple tasks, and you can see the results as we were showing. And between the variations of our R-GCN model, here we don't see really much. They all perform equally, more or less. We don't see a lot of difference, and this is because of it's the lowest complexity task. And in the next, in 2 slides, I will get to the highest complexity tasks that we design. But here, just pictorially, you can see on the x-axis, we have the 6 different pairwise tasks. And I'm showing here F1 score and hits at 1 to compare with the baseline, the AO. And hopefully you see that generalization gap that I was alluding to. And yeah, likewise, for its hits at 10 and mean rank, we'll be showing all of that pictorially from the table that you just saw. So this kind of proves our kind of hypothesis that in terms of generalizability and in terms of complexity of tasks, we also designed 2 more experiments. Now on top of, or in addition to subclass of and same as relations, we're including in the second task the 3 extra relation types, and in the third task, DS3, even more, even including intersection of and conjunctive properties. And here now you see that actually we need to include, to preserve performance, we need to include the variations, the rules, the RDFs metapaths, and that brings back for R-GCN, the performance falls across the board, and then including the metapath rules gains back that performance, and there's no AO, the baseline here, because as was presented in the paper, there was no straightforward way to support these complex, these levels of complexities with more relations types. Yeah, so we did a final set of tasks because we were wondering if how much data we need in terms of training these models to perform at the level they are. And then so now we're taking 0%, so no data, just random initialization, 25%, 50%, 75%, up to all the training set data. And here we're showing mean rank and F1 score. And in some cases, again, there's 6 separate tasks, ontology matching tasks. In some cases, you can get away with, depending on the complexity of the matching, even with 25% training data. I guess in case of OMIM to Urdu, you still get 93% or 90.93 score for F1 score. And then, yeah, of course, the results that were in the tables or the diagrams were using 100% training data. Yeah, so, and finally, coming back to the original use case that I showed, I memorized what these codes are. So we had, I think, the adenocarcinoma, basophil adenocarcinoma is in the middle. The ID 9436005, and the NCIT is also shown there. And what the point I'm trying to make is, so the inferred links are what our algorithm comes up with and adds to the knowledge graph. So if you go one node up from each, then you see it's kind of, oh, I have a pointer. Yes, so they're right here. This is the original graph. And if you go one, so if you were to do this lexically, hopefully I convince you that that's not possible or pretty hard. If you go one parent up and then you follow this track, you see that our algorithm finds this kind of connection through the parent. So hopefully that closes the loop on that. Yeah, and so just to summarize, we aimed to solve this ontology matching problem, and as I introduced earlier, there for each, in our case, in biomedical and clinical domain, there are many ontologies. Yeah, apologies. Yeah, there are many ontologies, and to know these relations between them, I saw this picture last year in Leiden, so I thought it would be fitting to include that, but to find how these all fit together, we're proposing this embedding-based R-GCN method that kind of preserves or handles morphological, structural, and semantic properties of these knowledge graphs. And we saw that by including these RDFs metapaths as like a shared common higher up ontology vocabulary, we can have these hybrid models that can handle any complexity level of ontology matching tasks. And we're still, I think, there's still, we like the vision here would be if we could have like these built for all, like under UMLS, have this this kind of system built in where everything is mapped or matched using these kinds of models, but it takes time and very challenging. Well, anyway, that's it. Thank you very much for your attention.
Yes, thanks a lot for this nice talk. I'm just wondering, how well can you capture if a term changes slightly in meaning? So not very dramatically, just slight meaning, and it's not reflected in the graph itself. So if you have just in the definitions and in some kind of metadata, there's a slight change in meaning. How well can you capture that, and is there like a measure for doing that?
Yeah, great question. That would have been an addition to this, because at the moment we don't do any kind of like NLP or syntactic or lexical analysis. This is based on node representations. But yeah, if that's a great direction to improve this. This is more a structure or preserving structural information. Yeah.
Hi, thank you. Excellent talk. My question is related to the one that it was just asked. the advance in scientific findings actually make the continuous changing of the terms. For example, in the field that I work in, glioblastoma, with new data, you change terms. So now mesenchymal is not mesenchymal anymore. It's better defined as gliosis and all these type of things. So periodically, the more advanced the technology, the terminology, to be more scientifically precise, it will change. Yeah. So how is this updating happening, in the ontologies, or how is that control? Is something that who is in charge of updating these things?
Yeah. I was trying to kind of clarify this at the beginning. I showed the 3 paradigms. So this is kind of by design. We're going with the paradigm that locally you can make changes. So then once that you freeze that, and now you want to match that with another ontology. So that's where we enter. Is that?
Yeah, but if I say, okay,
so you can change, but then we take that, and for us it's a fine-tuning problem.
Who will approve of that? Because anybody can say, I actually want to change this term. I don't think you. Of course, obviously, we're scientists, so you have proof to that. But I don't know if there are regulations. That's my question. Is there any regulation? No, it's just the scientific community self-regulating, I think.
Well, yeah, there has to be regulated and some approval process. Yeah, sure.
For the EMLS ontology, which was used in part, it's a scientific commission which changed it. And hopefully they think it out, not always. But as we'll see in the next presentation about mapping SNOMED CT to ICD-10, about the 2 most important ontologies in the hospital space, even with humans, it doesn't always go right.